Hello everyone and welcome to Control Engineering Tutorials. In this Control Engineering and Control Theory tutorial, we explain how to implement a sliding mode controller for a nonlinear system in MATLAB and Simulink. We will not go too deep into the theory of sliding mode control, and we will mainly focus on the implementation in MATLAB and Simulink. We will state the sliding mode control law and show that the control law satisfies the stability condition. As a demonstration and as a proof of the implementation principle, we will implement the sliding mode controller for a nonlinear pendulum system, which is a classical system for developing and testing control engineering algorithms. Here's the copyright notice and code license. This tutorial, web page, video lesson, developed code files and documents should not be copied, redistributed, or posted on public or private websites, public or private code repositories, or social media platforms. This lesson and all the provided study materials are strictly for personal use. Without the permission of the author, that is, without the permission of Aleksandar Haber, this lesson and the provided material should not be used for commercial purposes and for training of engineers working in companies. Then, this lesson and the provided material should not be used as lecture materials on online learning platforms and in university courses. This lesson and the provided material should not be used to train an AI algorithm or a large language model. Without the permission of the author, the provided code should not be used for academic research or for commercial purposes. Let's start with explanations. The pendulum system is shown over here. It consists of the rod, whose length is L, and there is a ball attached firmly to the rod. The mass of the ball is m. Then, the rod is suspended or supported at this point over here. The rod can freely rotate around this point. The angle of rotation measured from this vertical axis is denoted by theta. We assume that there is a control torque, denoted by T, that's used to rotate the rod. If we write the Newton-seconds law, we will obtain an ordinary differential equation describing the dynamics of this system. And after several manipulations, the dynamics is described by this equation. In this equation, theta double dot is the second derivative of theta with respect to time. G is gravitational acceleration constant that is equal to 9.81. L is the length of the rod. Sine is a simple sine function. Theta is the angle of rotation of the rod. M is the mass. And T is the control torque. Next, if we define A to be equal G over L and B to be equal 1 over ml squared and U to be equal to T, then we can write dynamics like this. The control objective is to design a controller and a sequence of control inputs U, or torque sequence, that will make sure that the angle of rotation theta of time follows a desired or reference trajectory denoted by theta d of t. That is, we want to find a control action that will make sure that theta follows a prescribed time trajectory denoted by theta d of t. We solve this problem by using the sliding mode controller. As always, the first step is to define or to introduce the tracking error. The tracking error, denoted by epsilon, is given by this equation. It is equal to the difference between the desired trajectory and the value of theta. Secondly, to define the sliding mode controller, we need to define the switching function or the sliding function. The sliding function is defined by this equation, namely, sigma is the notation for the switching function, c is a positive parameter selected by the user, epsilon is the error defined over here, and epsilon dot is the time derivative of epsilon. The sliding mode control is computed by using this equation. In this equation, B is the model parameter, C is the parameter of the switching function, epsilon dot is the first derivative of epsilon, theta d double dot is the second derivative of the desired or the reference trajectory, K is a new parameter that is a control parameter and that should be selected by the user, and SGN is a notation for a sine function. The sine function returns 1 if the argument is positive, it returns -1 if the argument is negative, and it returns 0 if the argument is 0. As mentioned previously, the parameter k is a control tuning parameter. In fact, there is a minimal value of this parameter that ensures that the closed-loop system is stable and that the sliding motion and the sliding mode are achieved by the controller. In the sequel, we will show that if k is greater than a, where a is the model parameter introduced over here, then the controller achieves sliding mode and sliding motion. That is, this equation over here defines the minimal value of the parameter k for the control system to work properly. We need to show that this equation is satisfied. In this equation, sigma is the switching function, sigma dot is the first derivative of the switching function, eta is a positive scalar, and this notation over here denotes the absolute value of sigma, that is the absolute value of the switching function. This condition is often referred to as the reachability condition in the context of the sliding mode control. The reachability condition ensures that the sliding mode is achieved in finite time, and it guarantees that a controller will work in the implementation. So let's show that this equation is satisfied. First of all, let's take the first time derivative of our switching function. As the result, we obtain this equation. On the other hand, we can simply substitute the expression for the second derivative of the tracking error in this equation, and we will obtain this equation over here. Then, if we substitute the dynamics in this equation, that is, if we substitute theta double dot by the expression for theta double dot given over here, and we substitute it over here, we will obtain this equation. And now you can see that our dynamics appears. Here is the parameter a, here is the sine function, and here is the b multiplying u. The next step is to substitute the control law over here. That is, instead of u, we will write this expression over here. And let's see what happens. If we substitute u, we will obtain this equation, then b and b can be cancelled, and we obtain this equation over here. Let's analyze what's happening over here. We can cancel this term and this term, this term and this term, and finally we are left with this term over here. Next, if we multiply this equation by sigma, we will obtain this equation over here. Next, we will use these two very well-known facts. First of all, if you have a variable multiplying the sine function of that variable, then you will obtain the absolute value. And that's precisely the property of the sine function that we use over here. Next, we can say that, or we can actually conclude that sigma multiplying sine theta is smaller than or equal than absolute value of sigma. How did we obtain this expression? Well, we know that the sine function, or better to say the absolute value of the sine function, is always smaller than or equal to 1. Then, by using this expression and by taking the absolute value of sigma, we obtain the final relation. Next, by using these two relations and properties inside of this equation, we will obtain this. We will see that sigma multiplying sigma dot is smaller than or equal to A multiplying absolute value of sigma minus K multiplying absolute value of sigma. Next, we can take sigma out, and finally we obtain this expression. From this equation, we see that if A minus K is strictly smaller than 0, or equivalently K is greater than A, then the reachability condition is satisfied, where the constant eta is K minus A. That is, we can observe that if K is greater than A, then this right-hand side is smaller than 0, and consequently the sliding mode controller will work in practice. Next, we proceed with implementation of the sliding mode controller in MATLAB and Simulink. And while selecting the control parameters as well as the parameters of the switching function, we will always make sure that this condition is satisfied, and later on you will see how other parameters influence the behavior of the control algorithm. Okay, let's start with implementation. The first step is to define the model parameters. For that purpose, let's open a new script, and in the new script, let's first define G to be equal to 9.81. Then, let's define the mass of our ball to be equal to 5. Then, let the length of the rod be equal to 1. Let's not forget semicolons. Then let's define the A parameter. The A is G over L. Then let's define B. B is equal to 1 over M multiplying L squared. And finally, let's define C to be equal to 3. This is the parameter of the switching function. And finally, let's specify K to be equal to multiplying A. Note over here that by choosing K to be equal to multiplying A, the stability condition of the sliding mode controller is achieved. Next, to simulate our dynamics, we need to assume two initial conditions. Namely, we need an initial condition for theta and theta dot. So let's specify theta 0 to be equal to pi over 6, and derivative of theta 0 to be equal to 0.1. Good. Let's select everything and let's press F9, and now all the parameters are in the MATLAB workspace, as you can see over here, and we can use them in the Simulink block. Okay, the next step is to start Simulink. So type over here Simulink and press enter. After starting Simulink, click on blank model to create an empty model that we will modify. Okay, so let's start. The first step is to model the system dynamics. Namely, if we look at the system dynamics, we will see again that the dynamics is described by this differential equation. And we need to model this differential equation in Simulink. What's the idea for modeling this differential equation? Namely, from this equation, you can simply express theta as a 2-time integral of the right-hand side. And that's the main idea. So let's go back to Simulink and let's do that. First of all, let's introduce the sine function. Double-click here and search for sine. Here it is. Okay. Over here, we will have theta getting in, and the output will be sine theta. We need to multiply sine theta by A. Double-click here and search for gain. And here's the gain. Expand the gain, double-click on the gain, and over here is the gain, type A. And you can see immediately that Simulink is able to access the parameter A defined in the MATLAB workspace. Click OK, and let's continue. Next, we need to add a summation block. Double-click here and search for sum. Here it is. Now let's rotate these ports of the sum block. How to do that? Well, there are several ways to do that. Double-click here, then move this vertical bar from the beginning until the end. Okay, and now over here we need to modify, since the first port should be with the minus sign. Here it is. Perfect. Actually, not like this. We need to do something else. Not like this, so erase this. The second one should be minus, and if you click on apply, now everything is fine. So connect this part over here and with this part over here. Now we have sine theta multiplying a, and over here we have with a minus sign. This part over here is the control input. Namely, we will need b and the control input u. So let's create a constant over here, b, search for gain, connect this part over here, double click on this gain, and put b over here. And you can see that b parameter is automatically recognized. Click OK, and let's continue. The input over here is the control input. Next, we need to integrate the right hand side over here twice in order to obtain theta. So let's do that. Over here, double click and search for an integrator. Here it is. Connect this part over here. The output of this integrator block is actually theta dot. The input is double theta dot. And we need another integrator. So click here and search for an integrator. Here it is. Connect this part. And then the output over here is theta. Simply connect this output to the input of the sine block, and that's it. And over here we can click on this block and we can type theta over here, and over here you can also do the same thing. You can type d theta. Okay, perfect. Now we have our dynamics. However, over here we need to enter the initial conditions. Namely, in our MATLAB parameter script, we have two initial conditions. So double click over here, and as initial condition, type d theta 0. And you can see that d theta 0 is recognized. Click OK, double click over here, and simply type theta 0 or theta 0. And here it is. Click OK, and that's it. Good. Next, we need to implement our control law. But before we implement the control law, we need to define a reference trajectory. Double click over here and search for step. That is, in this tutorial, we will assume a step reference trajectory. Double click here, make sure that the step time is 0, since we want our step signal to start at 0. And let's see and let's analyze our control algorithm. Where it is? Here it is. To compute this control algorithm, we need epsilon dot, that is the first derivative of the error. We need second derivative of the reference trajectory, and we need sigma as well as these parameters. Now, if you expand the expression for epsilon dot, you will see that the epsilon dot depends on the first derivative of theta dot and the first derivative of theta. From this, we assume, or actually we conclude, that we need the first and the second derivative of theta d. So let's create these derivatives. Double click here and search derivatives. Here it is. Connect and double click again and search derivative. Here's the second derivative. Now we have the first and the second derivative of the reference trajectory. Good. Next, we need to add over here an MUX block. Namely, we will need to group several terms. So double click here and search MUX. Click over here and specify the number of inputs to be equal to 5. And expand this block. Good. The main purpose of the MUX block is to group all the signals inside of a vector. Then this vector will be provided as an input to a block that we will define later on, and that will implement our control law. So let's create the connections. The first port is xd or theta d. The second port is the first derivative of theta d, and the third port should be connected to the second derivative of theta d. Good. Then the fourth port should be connected to theta, or theta, however you like to pronounce, and the last port should be connected to theta dot. Good. Next, we need to implement the control law. To implement the control law, we will use the so-called MATLAB level 1 S functions. Consequently, over here, we will define that block. However, before we create the S function block, we need to create an S function in MATLAB. Consequently, go back to MATLAB and let's create an S function. Luckily, MATLAB usually have a template for MATLAB functions, or better to say for S functions. How to find this template? To open the S function template, type over here open and then type under single quotation sfun tmpl. Again, sfun tmpl. And if the template exists on your system, this file will be open. However, I noticed that some other versions of MATLAB don't have S-function templates. Don't worry about that if you cannot find this template or if the open command returns an error. I will provide a link to a special written tutorial with all the codes, and you can use my code for the S function. So let's start. First of all, over here, let's erase everything. That is, let's erase these comments from here to here. Good. Next, we need to provide the input parameters to our S function. What are the input parameters? Namely, to implement the control algorithm, we need to specify several things. First of all, we need to specify the model parameters. So what are the model parameters? The model parameters are A, B, K, C. How to specify these model parameters? Well, in the parameter list, we will need to specify over here B, then comma, K, then comma, C. Good. Let's analyze this file. This S function defines everything what a block inside of a MATLAB Simulink simulation is doing. First of all, over here, there is an initialization step. So let's perform the initialization step. You can see case 0, and then you can see this function. Press Ctrl C to copy this function name, then press Ctrl F to find the function and find the definition over here. And let me erase these comments. So let's see. numCont state is the variable that specifies how many continuous states we have. Since our control law is just a static control law without dynamics, the number of continuous states is 0. Similarly, we don't have discrete states, consequently leave this at 0. How many outputs do we have? We have only a single output, and that's our control law. Consequently, modify here and specify 1. How many inputs do we have? We have 5 inputs. These 5 inputs are specified or defined by the MUX blocks. How many direct feed-through terms we have? We have only a single direct feed-through term, and leave this other variable as it is. And that's it. We don't have any initial conditions since the controller is completely static. Okay, let's continue further. Next, go back at the beginning of the S function and let's see case 1. We don't have any derivatives in our case, and consequently we will leave case 1 as it is. Similarly, since we are not dealing with discrete time system, we don't have any updates over here. However, we need to modify case 3. That is, we need to modify this function MDL outputs. First of all, let's specify the parameters over here. Namely, here we need to pass the parameters b, k, and c, and then let's go to the definition of this function down. Here it is. And over here we need to modify again the parameters. The parameters are b, comma, k, comma, c. And over here, to save time, I will simply copy and paste the content of this function. Here it is. This function will actually compute the control input u. U is the input to the block. That is, u1 is theta d, or the reference trajectory, or if you want to call it, you can call it as a desired trajectory. Then u2 is derivative of theta d, u3 is the second derivative of theta d, u4 is theta, and u5 is first derivative of theta. That is, these variables correspond to the mux block and the output of the mux block. Then, to implement the control algorithm, as you can see from this equation, we need to compute the first derivative of the error, we need to compute sigma, that is our switching function, and we need to use theta d double dot. So let's do that. First of all, let's compute the error. The error is difference between theta d and theta. The first derivative of the error is the difference between derivative of theta d and u5, which is derivative of theta. Then over here, we define sigma, or our switching function. It's simply equal to c multiplying error plus the first derivative of error. And over here, we implement the control law. We have 1 over b. You can see 1 over b. Then we have c error dot, c first derivative of error, as you can clearly see here. Then we have theta d double dot, or the first derivative of theta d. Then we have k, which is the control parameter, multiplying the sign of sigma, and that's it. Once we compute control, we simply set the output of this function to be equal to control, and that's it. Now, let's save this function. First of all, to save this function, you have to modify this template name. So let's call this template as control law, or template function as control law. Then click on save. Here, save as, or let me just now cancel this. Oops, I made an error since I cannot save in this folder. Save as, and then let's save it somewhere where you like. I will save it on my C drive. In fact, I created a special folder for this project. Here it is, and I will call the function or the file as control law. Here, it's very important that the name of the file matches the name of the function. Namely, if you use the name control law over here, you need to use the same name over here and click on save. And that's it. That's it. And over here you can see the control law. Let's also save this file, and let's call this file simply as a script. And that's it. Good. Let's continue. Next, we need to embed this function, that is our control law, inside of our Simulink block. How to do that? Well, to do that, let's go back to our Simulink block over here. And inside of this Simulink block, double click and search for S function. Here it is. Double click on the S function, and over here you need to specify control law. Now, to make sure that Simulink is properly linking everything, click here on edit. And if everything is linked properly, you should automatically see your control law M file over here. If it's not, then you need to add this folder to the path. To add this folder to the path, click on home, click on set path, click on add with subfolders, and over here you can basically click and find your folder. So here it is. Let's find it. Here it is. Select the folder, click on close and no. And that's it. Okay, let's go back to this Simulink block. Double click here, click on OK. However, the story doesn't end here. Namely, if you look at the control law, you will see these parameters, and these parameters have to be passed to the function. So copy these parameters, go here, double click on the control law, and paste them over here with commas. That is, we're specifying B, K, and C. And note over here that the values of B, K, and C are actually read from the MATLAB workspace since we defined them over here. Let's continue. Let's connect this block with this part, actually over here. The output should go inside of this B gain, and the input should be connected to the output of the MUX. And that's it. Now, let's verify that our implementation works. To do that, simply click on Run, and everything should be simulated. No error. However, we need to plot some results. To plot the results, double-click here and search for MUX. Then connect the first port to the theta D, the second port to the output. Then double-click here, search for scope. And click here, connect this part, then run again. And double-click over here to see what's happening. Click on View, Legend, and you can see step signal, the yellow line, and you can see theta, our response, and we can see that our sliding mode controller is able to follow a step signal. Good. Next, let's export the simulation data such that we can plot more graphs. To export the Simulink data to the MATLAB workspace, we need to use the outport blocks. So double click here and search for outport. Here it is. First of all, let's outport theta. Consequently, connect these two lines. Good. Double click here and let's call this signal as theta. Next, let's export d theta. Double click, search for outport, and connect to d theta. Double click here and give the signal name to be d theta. Next, we need to export the trajectory and the first and the second derivatives of the trajectory. Consequently, click here on outport, connect this block to trajectory, double click here and search for, and actually type, let's choose the name theta t. Good. Then click here and again outport, connect this block to the first derivative of theta d and call this as d theta d. Then let's introduce the fifth one, again outport, connect this to the second derivative of theta d, and over here type dd theta d. Good. Click on OK and let's continue. Then over here we need to export the control law or the output of the control algorithm. Double click here and search for output and connect this block to this part over here. Double click here and call the signal simply as U, and that's it. Now let's simulate everything again such that all the variables are in the MATLAB workspace. Then over here let's go to MATLAB, and to save time I will simply copy in or actually paste the piece of code that I wrote previously, and here it is. So let's analyze what this code is doing. First of all, if we now type whos inside the MATLAB workspace, we can see this out. If you type out, you'll see that it's a data structure. Then if you type out, y out, you can see everything that's being exported. Theta, d theta, theta d, d theta, d theta, and u. And consequently, we can access all of these time series. To access theta, we need to type this, and I will store it inside of theta. To access the derivative of theta, we will type this. To access theta d, I type this. To access the first derivative of theta d, we use this. To access the second derivative of theta d, we type this. And to access the control input, we need to write this. Next, we define the error. We define the first derivative of the error. Then over here, I'm defining a sigma line. This sigma line is the sliding surface. Then I'm defining the switching function. And over here on figure 1, I'm plotting the sliding line or the switching surface, and I'm plotting the error and the first derivative of the error. The error will be on the horizontal axis and the first derivative of the error will be on the vertical axis. This is the first figure. So let's generate this figure. And let's see what's happening. And here it is. This is a very important figure. We can see that we start from here, then the controller pushes the error and the first derivative of the error to this line, that is to our sliding surface, and then the controller always keeps the trajectory, or better to say the error trajectory, on the sliding surface. And then finally you'll see that we converge to 0. This means that the controller works as it should work. Next, over here, we are using this piece of code to plot the control input. So let's plot the control input, and you can see how the control input behaves. Honestly speaking, this is not desired in practice. This is mainly because that rapid switching of control input will excite the high frequency components of your dynamics, and these high frequency components are usually not accurately modeled, and you might also experience resonances. Consequently, you need to kind of smoothen out this signal. However, this is a story for itself that we will not cover in this video tutorial. Next, on figure 3, let's plot theta d and theta. That is, let's plot our control performance. And you can see nice graph. The red line is the control trajectory, and the dark line is the reference trajectory. And finally, on figure 4, we plot the value of sigma. You can see how the value of sigma quickly goes to 0. This means that we live on the sliding surface. Okay, that's all for today, and thanks for watching.